In this video, I'm going to explain about specific heat capacity. So as you can see, this is the experiment that you will need to use to measure the specific heat capacity. They've clearly got a joule meter here and a 12-volt supply, and here you have a heater which is going to heat up this copper block, and they're going to measure the temperature change to measure the energy. Now this copper is probably going to be 1 kilogram, because specific generally means 1 kilogram, and the specific heat capacity is the energy required to raise 1 kilogram of substance by 1 degree C. So you need to know that definition for your exam. Now the first question is asking, the initial temperature of the copper block was measured, the power supply was switched on, the energy transferred by the heater was measured using the joule meter, and the temperature of the block was measured every minute. The temperature increase was calculated, and figure 2 shows the student's results. So it's asking us, use figure 2 to determine how much energy was needed to increase the temperature of the copper block by 35 degrees C. So if we start off at 0, going all the way up to 35 degrees C, so we need to then move a line across here and then plot that down to an accurate point, which would be 35,000 joules. So obviously on your exam you need to do that accurate with a sharp pencil and a ruler. The next question says the copper block has a 2 kilogram mass. So we know the mass now, so this is the specific capacity. If it's 2 kilograms, then we know that energy is equal to mass times specific heat capacity times the temperature change, which is theta. So we need to rearrange this for C. So if we divide by m and we divide by theta on this side, we're going to do the same on the other side. So we've got m times theta, that cancels and that cancels. Therefore we've got C is equal to the energy divided by the mass times by the temperature change. So what's the energy we've just worked out? Well, that's 35,000 joules, and we're going to divide that by the mass and the temperature change. So the mass, it tells us here, is 2 kilograms, and we're going to multiply that number by the temperature change, which we know is here. It's gone from 0 to 35, so that's 35 degrees. So what does that equal? Well, that equals 466.7. And the unit for specific heat capacity is in joules per kilogram degrees C. Now if you forget them, you can just look at the equation to work that out. So specific heat capacity C, if I just write that down here, C is equal to the energy, which is in joules, and we're going to divide that by the mass times by the temperature change. So joules, this line represents per kilogram multiplied by degrees C. So this tells us the units for specific heat capacity if you forget. Joules per kilogram degrees C. Right, the experiment does not give the correct value for the specific heat capacity of water, suggests a reason. Now whenever it's talking about errors or something to do with a value that is not correct, it's because this is going to be heating the surroundings. So bear that in mind, as it's a really common question and something you would have seen on the level 1 questions. So energy is transferred to the surroundings. Okay, so an electric immersion heater is used to heat the water in a domestic hot water tank. When the immersion heater is switched on, the water at the bottom of the tank gets hot. Right, so what's it going to ask us in this question? Graph A shows how the temperature of the water inside a hot water tank changes with time. The tank is not insulated. So the temperature starts off here, which is around 57 degrees C. The temperature of the water falls at the fastest rate just after the heater switches off. So it's gone from 57 and it's gone down to 50 degrees C. So it's asking us to explain why the temperature rate of change is greatest at the start. Now the reason for this is the greatest emission of radiation is going to be when there is the greatest temperature difference. So it's the temperature difference between this and the outside air. So let's imagine the outside air, which is outside this heater, is 20 degrees C. Well, at the beginning, it's 57 degrees C. So the difference between those two is 37 degrees. As it starts to go down in temperature, it goes down to 50, the rate is going to decrease because this temperature difference is lower. So you're going to get a much faster rate because you're going to get more emission of radiation when there is a greater temperature difference. So the water tank emits radiation at a faster rate when there is the largest temperature difference. And that temperature difference is between the tank and the air outside it. So just be specific about that and put that on at the end. Okay, so to heat the water in the tank from 50 to 58 degrees C, the immersion heater transfers 4,032 kilojoules of energy. So again, we're trying to work out something using the specific heat capacity equation, So energy again is equal to the mass times specific heat capacity times the temperature change. So again, we're going to have to rearrange this equation. We want mass, so we're going to get rid of these two. We're going to divide by on this side, so we do the same on the other side, and those are going to cancel. So mass is equal to energy divided by specific heat capacity times the temperature change. So what's our energy? Well, that's 4,032 kilojoules, so we need to get this into joules. So that must be 1,000 times larger, so we know that's 4032000. I'm going to divide that by the specific heat capacity, which is 4,200, which it says here, and we're going to multiply that by the temperature change, and that clearly is gone from 50 to 58, so it must be an 8-degree change. So if we do that sum, we get a mass of 120, and the unit is in kilograms. Okay, according to kinetic theory, all matter is made up of small particles, so particles are constantly moving. Now remember, no matter what it is, the particles have to be moving. Even at the very, very coldest parts of space, you still get particles vibrating, just a lot slower. Right, 1 kilogram of gas has a much larger volume than 1 kilogram of a solid. Use kinetic theory to explain why. Right, for this question, I'm just going to talk about all the key points relating to solids and relating to gases. Okay, so in solids, there are strong intermolecular forces. Okay, and the particles are therefore held closely together in a fixed lattice. Now remember, a lattice is when you can draw a grid through the particles, so it is in this lattice shape. In a gas, there is weak intermolecular forces, or weak forces between the particles, however you want to call it. And because there's these weak intermolecular forces, the particles are free to move and are therefore much further apart. Okay, now this is because of their high energy collisions. Now while we're on this topic of solids and gases, even though it's not related to this question, because it is about kinetic theory, let's just say that solids have a low kinetic energy, which is a movement energy, and gases have a high kinetic energy. So the kinetic theory is the theory of movement of particles in solids, liquids and gases. And solids vibrate and gases move freely with lots of energy. Okay, this question is not specifically on the specification, but it's important you recognize what's going on because it's about energy and it's a type of question they could ask you to test your understanding. So how can you tell from the diagram 2 that the liquid is evaporating? Well, you can clearly see particles that are escaping the liquid. So these are liquids because the particles are touching, but they are random, and these particles are escaping the liquid. So evaporation is when particles in gases escape the surface of a liquid. So particles are escaping the surface of the liquid. Okay, the temperature of the liquid in the container decreases as the liquid evaporates. So again, this is not something you specifically have to know about, but I'm going to explain why temperature decreases when things evaporate anyway. So if you imagine that these particles that have escaped the liquid have got high energy, they are taking the energy away from the liquid. So if the high energy particles escape, they are going to leave the particles that are left behind with a lower average kinetic energy. And if the particles left behind have a lower average kinetic energy, that means their temperature must be lower than it was before, because temperature is a measure of the average kinetic energy of the particles in a substance. So if the kinetic energy is decreased because some of the particles have escaped, then the average kinetic energy must decrease for the liquid. So we're going to say that as particles escape liquid, and remember these are high energy particles, so as particles escape liquid, they take the energy away, leaving the remaining particles with a lower kinetic energy. If the average kinetic energy of substance is lower, the temperature must also be lower. Okay, and here are the answers. So if you want to just look at the mark scheme, I'll leave this on for a few seconds.